about max and padding. I'm asking literally just about CBC mode. I'm not asking about the scheme you guys implemented. You guys implemented CBC mode with some padding scheme that is specific and with a MAC. Forget about that. Just generic CBC mode. Yeah?
The person decrypting will just get C1.
Good. So this is called a truncation attack. And literally all it points out is that in plain CBC mode, before you add backs and padding, deal with that stuff, you can chop off the end blocks of the message, and then you can send the message to be decrypted to the point of, from the point of view of the person decrypting it. All that will do is give them a perfectly valid plain text up until the point where the message has been chopped. Okay, so this is called a truncation attack. CBC naively is vulnerable to this. I hope this is obvious to you. Just want to make sure it's clear. There are other attacks you can do if I have two CBC mode two different messages. Is there any way I can like stick them together with the same key? Two different CBC ciphertexts, and they contain two different plain texts, and I want to like concatenate them in some way. What happens? Yeah.
Isn't there different IVs, so you can't do that?
Maybe, but think about it a little deeper. Yeah.
You can decrypt all the way up to the first block.
Okay, what will happen then?
Well, because you don't have the IV, you can't decrypt the first block, but you can decrypt everything else.
Okay, so I have IV1, C1, I'll call this C11, C12. Okay, this is one ciphertext. I'll call this C1. Oops, my one looked like 2's, that's a problem. Okay, this is my first ciphertext, and this is my second ciphertext, which has a different IV, IV2, and we'll call this C21, C22. Okay, just happen to be the same length. That's not really important right now. And what I know is that they encode some plain text, 2-block plain text. I don't know what they are. What happens if I assemble the following synthetic? If I get both of those things and I assemble the following synthetic ciphertext: C11, C12, C21, C22. Okay, so this is a 1, 2, 3, 4 ciphertext block plus IV ciphertext. How is that going to decrypt? Yeah.
Well, you'll be able to decrypt C22 and C12, but you won't be able to get C21 and C11.
What do you mean by won't be able to? So you're saying that this will decrypt to M, the proper plain text. This will decrypt to the proper second block of plain text. Taking the first one.
The M1, the C11 won't decrypt at all.
This one won't decrypt?
Yeah, it'll be garbage.
Wait. I just took the first 3 blocks from the first ciphertext.
Oh wait, you do have the ID. Okay, I was.
Yeah, no, it's the same. It's the right ID. I'm using
okay.
IV1, C11, and C12.
Yeah,
so literally.
Okay, so C21 is the only block there that won't decrypt.
Oh, okay. So you're saying this one will decrypt, okay?
Yeah, because because the decryption scheme for CBC requires the previous cipher block. It doesn't require the IV.
Good. Anyone disagree with him? Anyone have a different bet for how it's going to decrypt? You all agree? Or you're all just like not willing to give me an answer? Which of those two?
Just reading the board, just want to make sure I'm looking at, they both have the same IV or they both have different IVs?
Different IVs. Different messages, different IVs. Remember, don't use the same IV twice when you encrypt a CBC.
Right, I just...
So we're literally throwing away the second IV. And we're butt splicing the rest of it. Or we can even put it in the IV. I don't know. We can do something. But for now, we're not. We're just taking the last 2 blocks of the second ciphertext and we're butt splicing them onto the first ciphertext. Okay, so what do you think is going to happen? Do we have an agreement or do we have questions? Okay, we're going to call this C prime, just for fun. How does it decrypt? So the claim that I've heard is this will decrypt as follows, and what's going to happen here? Okay, we'll just, boom, something terrible is going to happen. Okay, anyone want to dispute this?
Can I XOR C21 with IB2 and C12?
Well, you can't XOR the ciphertext. You would have to XOR the underlying plain text. And I don't see a way to do it. You can work it out on paper and see if you can find a way to do it. This naive kind of thing, which is basically, it's called a chop-chop attack, is literally just butt splicing CBC mode ciphertext together. It works. It just leaves a seam. And the seam is that, yeah, one value gets trashed, but the next block is fine. In fact, if these were 100 blocks long each, you could put 200 block messages together, and yeah, you would have 1 block of trash, but they would concatenate. So CBC is very malleable in lots of interesting ways, right? It has all these problems. Truncation attacks, it has chop attacks where you can like put two different ciphertexts together to make yet a new ciphertext. And then somebody was asking, how else are they malleable? And I'm sorry, this is a very long-winded answer to a very short question. How else are they malleable? What else can I do to change the underlying plain text of a single CBC ciphertext? Besides truncation, besides chop. Yes, anyone? There is nothing I can do. With XOR, is there anything I can do? Come on, guys.
Can you change the ciphertext?
I can definitely change the ciphertext. Give me a specific way to change it.
If you change a bit in like C1,
Good. What's going to happen?
that gets XORed with M2.
Good. Okay, good. So if I change a bit here, right, what's going to happen when this gets, what's going to happen to M1 when this gets decrypted?
It's garbage.
Okay, so this will get trashed, but as you're pointing out, changing one bit here, when the decryption happens, the way the decryption works is C2 gets decrypted through here, and it gets XORed with C1. So if I flipped one bit here, then this will be fine, and the output of this XOR will be exactly the same, except for one bit will be different. So if you want to alter CBC mode ciphertext, you can flip bits. You can XOR. Another way of saying this is I can XOR C1 with any vector V, and the end result will be that I get, instead of M2, I will get M2 XOR V. And so that is how I can change a CBC ciphertext. Yes?
At what stage are you assuming that you changed that ciphertext? Are you assuming that it's already been created and now?
I am saying that somebody has sent a ciphertext over the wire, and I've intercepted this ciphertext, and I want to alter this ciphertext so that I get a different ciphertext, and I send it on to somebody else to be decrypted. So I could be a man in the middle intercepting things from the wire, or alternatively, and this is a very common one, let's say you're a website, and you send down an encrypted message to your browser, and then when the browser comes back, it sends down the ciphertext. The browser sends back this ciphertext. Why would that happen in the context of web browsers? Jeez, I shouldn't have run here. I'm gonna keep going. Why would this happen? Why would a website ever want to send you an encrypted blob of data to be stored that you would send back? Where does that come up in the world of web security?
Certificates.
Certificates maybe, but actually it's not what I'm thinking of. Something else. When does your web browser store blobs of data for websites? Cookies. Good. What are cookies in general? Besides blobs of data.
Mobile configuration files?
I mean, sure, they could contain data, right?
Typically, it's just a token that identifies that session.
Good.
So it's enough that it says, okay, for this token, associate this session data.
So one way of building a website is to basically say, keep a database, and the database has like an identifier that says, you are user number 53967, and my database will identify everything about your session with that token, and then your cookie will literally just be a blob of data that says, here is who you are. You're 53967, the next time you visit, you'll send back that cookie and the website can look it up. Good. Why would you want to replace that database with something that sends encrypted data down? What would be the possible advantage of storing data encrypted? Instead of keeping it locally in a database on a web browser, why would you want to send it to the client encrypted instead? Why do you want the client to store that data instead of putting it in a database? What's the problem with databases? Slow. Good. You have to keep a freaking database, and every time somebody visits your site with a cookie, you have to look that cookie up at the database to get their session information. Why wouldn't you want to just store the session information in the cookie in the browser and avoid a database lookup? Doesn't that make life a lot easier?
Oh, what if it gets intercepted?
Good.
What if it gets changed en route?
Very good. So there are two possible things that can go wrong. One is that the person who's storing that cookie now can see all that data. If it's meaningful data, they can look at it. And maybe you don't want them to do that. So what do you do about it? Well, your website will now encrypt it under some key, K, that it stores, and then even if the person lists their cookies and tries to like learn stuff about the browser, what's going on in their browser, they will not be able to see the data. That's great. What's the other threat that might happen in this scenario where you're storing encrypted cookies in somebody's browser? What else might the user want to do?
Change it?
Why would they want to change it?
Well, for example, you might have a user that is a regular customer of a website, but if one of the fields in that session data is admin equals 0.
Good.
You can change it to admin equals 1.
Very good. If you have a database, you can store all this information. You can trust your own database. But if you're offloading, storing that data onto a browser, you can't trust a browser. The person could look at that data. They could change that data. They could change their user ID to make themselves into somebody else. They could change their privileges to make themselves an admin. If you're a bank, they could change their bank balance to make them worth, billions of dollars, whatever they might do. And so what else might you want to do to this encrypted cookie to make sure they can't do that?
Signature?
Okay, one thing is you could sign it. What else? What other tool do we have? A Mac. Good. So this is actually how many different websites work. If you look at your cookies, you might see some very big, random looking ones that don't look like identifiers. And chances are what those contain is encrypted and hopefully MAC'd data that the website has decided to store on your browser. And so what I was trying to get at is now let's say I intercept one of those cookies because you gave it to me, right? I'm not a man in the middle. The decryptor is this website. I can actually send back that cookie to the website. And let's say maybe the website, I can alter it using, maybe all they did was encryption, CBC mode encryption, no MAC. Okay, now I happen to know the right position inside of this ciphertext where admin equals X is listed. Because I can mull CBC mode ciphertext, I can maybe flip that bit from 0 to 1 just by XORing the right place in this ciphertext. And many websites which are not developed by good people, smart people, will actually just use something like CBC mode encryption with no MAC. And now you can basically change your privileges. So here's a scenario where the ability to mull ciphertext really, really, really matters, and why it's important to use things like MACs if you're building websites. Okay, many different packages like ASP.NET, things like that. They all provided cookies that worked like this, and they were all broken. And over the years, they're better now because they've been attacked so many different times. Okay, so there are lots of scenarios where malleability matters, as well as confidentiality. Okay, does that answer the question about how you can change, very exhaustively answer the question of how you can change ciphertext? All right, good. Any news?
Apparently the Yahoo hack was bigger.
How many people?
Everybody.
Everybody? 7 billion?
Well,
3 billion. Do you actually think 3 billion people use Yahoo?
Yeah.
So like
There may
1
have
billion
been 3
people.
billion accounts.
I mean, Yahoo was a huge email provider at one point in time.
Yeah.
So,
So what's the scariest thing about losing your Yahoo account in 2017?
the fact that they have all your emails from 2004.
Yeah, maybe, but would you really care about your emails from 2004?
Their bills, yeah.
How many people used your Yahoo account to sign up for your Gmail account? Maybe you guys are looking up. Okay, that might still be your recovery email.
Well, I actually have a Pactel account, so I think
Okay.
it's weirder. I don't know.
I'm not sure if that's better or worse, but whatever.
It's the predecessor.
Okay, so losing your Yahoo account could be really bad. For some people, maybe a certain generation, you guys all seem like you started your Gmail existences a little later than me. But yeah, this kind of thing is worrisome. Actually, does anyone know the story of what happened at Yahoo, aside from the fact that they got hugely hacked? At the same time they got hacked, there was a big scandal because it turned out that the US government had installed, with the permission of Yahoo executives, but not with the permission of their chief information security officer, a backdoor on a bunch of their servers, basically a rootkit that had been going through a whole lot of email and looking at communications. And so the chief information security officer and the security team found this rootkit, freaked out, thought that they were being attacked again, and quit the next day. So Yahoo has been a mess since before and since after. Yahoo is terrifying.
Did they get bought yet?
What's that?
Did they finally get bought? I can't remember. So
I think they got bought, didn't they, by Verizon or something?
Right.
Yeah. Oh, good. That's great.
At least they produce TV shows now.
What's that?
At least they produce TV shows now.
Oh, yeah. That's right. Yeah, the Yahoo News. Good. What else is happening?
So Equifax announced that millions more than they originally had thought.
But really, what's a few million, right? 2 more million or something like that? We did have a breach count, didn't we, at the beginning of this class?
Yeah, 500 years ago.
Yeah, I think we just blew past it, didn't we? We just got another billion from Yahoo. So maybe we need to revise our numbers upward. All right, okay. What else has happened that is not Yahoo or Equifax?
There's at the University of Buffalo, I believe, there's a team of researchers who made a heart signal as a password.
Huh. Interesting.
So it uses shape and beat and frequency, and apparently it's completely unique.
Interesting. Okay, do you think that's a good biometric?
Not really.
Why not?
Because I mean, it's kind of hard to access and to have, like, it's not gonna be cheap to. Like,
Well,
scan
can you
your
get it
phone.
with like an Apple Watch? Maybe. Yeah, I mean, this is really interesting. So this idea of doing biometrics, like internal biometrics, like to verify yourself is a really interesting idea. We don't know how secure it is, but I mean, this is like an active area of research. It's really interesting. Yeah.
Does this come with a follow-up question of how often you can change your heart rhythms?
Yeah, if your heart rhythm is stolen, you're kind of screwed with that. Yeah, so maybe that's a worry. Actually, this is a big problem in biometrics. How do you store biometrics securely so that you can verify them, but you can't, you know, how do we do it with passwords? How do we store passwords so that if somebody steals your password database, remind me quickly, you don't at least hopefully lose all the actual password. But you can still
Salted
verify.
hash?
Right, you do a salted hash. Can you do a salted hash of a heart rhythm?
I don't see why not.
Okay, but what, like just a simple like SHA-256 salted
So
hash?
you do some kind of digitization of your heart rhythm, so it becomes, in essence, a very long password.
Okay.
And then you do a salted hash of it. And
But what is the one thing about fingerprints or heart rhythms or even iris scans that's a little different than passwords? Like, what is the one difference?
It's not fixed always.
Yes, you might get a measurement that's like very close each time, but might be a little bit off, so it might
Right.
be a little fuzzy. And so there's actually a bunch of research in building like fuzzy hash functions that like will give you a consistent hash output, even when they get slightly different input. So there's this whole area of biometrics that deals with that. But yeah, I mean, essentially, this is a big question: is can you get enough entropy from these things to build like fuzzy hash functions? So, good. Anything else going on in the world? Okay, good. Call that a pretty successful one. All right, I wanted to talk about projects. After class, I'm going to be putting up a list. I didn't want to put it up before because I don't want you guys to look at them. And I promised you guys, I'm sorry, there's a reading that's really important, which is like 20 years of attacks against RSA, and that's also going to go up. Among the ideas, I just want to briefly discuss this project in class. First of all, it's a group project. The goal is to really start after the midterm or after the midpoint of the class and really spend your last few weeks doing something really good. Now, the project can consist of 1 or 2 or 3 different things. Some projects are like written reports. Some people are like, I really want to investigate some topic thoroughly. Great, that's fine by me. Sometimes what people do is they do a more exhaustive project and they give a presentation. So last year we had some people actually go out and try to investigate the Johns Hopkins identification cards and try to figure out if there were patterns and to see if they could like actually enumerate like all of the people at Johns Hopkins. And yeah, it was a disaster. The project was not a disaster. It was Johns Hopkins is a disaster. So that turned out to be kind of interesting. But the things that I'm really excited about are if you can tackle like a new kind of area or an area where I think there's like some kind of research or maybe like a potential for doing something cool, and ideally actually produce like something concrete, like a piece of software or like a demo that you could actually have. And those are the kind of projects I really want to steer you to. Some of the things that I want to work with in this class are, so let me give you 2 examples of projects, one of which is I'm a little worried that you guys might get arrested if I have you do, so this is the one. Okay, 2 examples of projects. So one simple project that I think would be really interesting for a group to work on is to look at password managers and actually try to build a password manager that's a deterministic password manager. Deterministic meaning that like from a master password you derive all of the the ultimate passwords that would be stored in the vault, so you don't have to store anything, so it would be completely offline. These do exist, and so the question is there like kind of a more interesting spin on that kind of project you could bring to sort of make something more usable and investigate like not only the crypto you need, but also kind of the usability properties. Another project that I'm interested in is, and I'm just proposing, is right now you guys are aware that ransomware has this problem. It's sort of weird to say ransomware has this problem, but ransomware has this problem that a lot of people pay ransomware and they lose their money but they never get keys. And so one of the questions I have been posing to classes is, what is the future evolution of ransomware? How do you make ransomware that is actually basically a fair ransomware, which guarantees that if you make a payment, you would actually get the decryption key? And so this is kind of a creepy question because it seems like in one sense it's kind of helping ransomware developers. But on the other hand, it's kind of interesting as researchers to figure out like what is actually possible to do in this area so we can anticipate it when it actually comes and try to think about countermeasures for it. And so this kind of thing, like figuring out how to make things like that, are interesting to me as long as you guys don't go out and like deploy ransomware and like let it loose on the internet. And so that kind of thing would be interesting to me too. I have a list. Let me just see if there's anything else I can give you a good example of quickly. What I really want to avoid is you guys kind of like going out and making your own version of SSH, because we have SSH and that's not super interesting to me. Let's see. Okay, yeah, one last idea. There is this new area of encrypted databases. And so there's a whole bunch of work right now, these encryptDB, that are databases that encrypt information but still allow you to sort and search. And the way they do this is by weakening the encryption. So you have encryption that is order preserving. So the ciphertext may be encrypted, but like if you sort them, they still preserve the same order as the original plaintext data. And so there's been a bunch of work actually trying to implement attacks on these systems and see how much data that leaks. And so I think there's some really interesting work, like to download one of these things like Google's BigQuery, encrypted BigQuery, and actually see if you can implement some of these attacks and recover data under realistic scenarios. Yeah?
So is this a database that, it's an encrypted searchable database?
Encrypted searchable database, yes.
Okay.
Yep, and it exists, you can download it.
Well, I remember hearing something about this 2 years ago, because one of my professors in undergrad was doing work on this concept on the cloud level.
Yes.
And I don't know where it went from.
Yeah, I mean, the question is, when you actually start implementing this with like fake medical data, how much data leaks? If I can, sort, how much can I learn from the ability to sort? How much can I learn from the ability to search? And there's some academic work on this, but it's still really interesting and open because it depends on the kind of data and the people you're putting in it. So there's actually a lot of kind of neat cutting edge work you can do to see how secure these things are. So these are 3 examples. There'll be lots of other examples. And the idea is for you guys to be creative and come up with things to bring to me that would be different. So I'll put up some suggested ideas. You guys get together. I told you to think about teams, and we'll go from there. We'll talk Monday, and hopefully you guys can start actually coming up with an idea of what you want to do. Okay, today we're going to talk about public key crypto. We're going to talk. We've already started talking about public key crypto. We talked about Diffie-Hellman exhaustively, maybe to the point where you hate Diffie-Hellman, never want to talk about it again. But Diffie-Hellman's incredibly important because Diffie-Hellman is an example of really the first public key crypto we developed. And what kind of protocol is Diffie-Hellman? What is the class of protocol? Key exchange or key agreement. Good. So we have one thing that we've talked about so far, which is key agreement. Okay. So key agreement. What's another public key algorithm or class of public key algorithms we care about?
RSA.
Well, that's a specific algorithm. What's a class? What class does that fall into?
Asymmetric key agreement.
Good. Not key agreement.
Key exchange.
We already have key exchange. Key agreement, maybe I should say exchange. What is different about RSA from Diffie-Hellman?
Public-private keys.
Diffie-Hellman has public and private keys. It's a public key protocol. What is different about RSA?
It's based on factoring.
Too specific, but right. What is the class that it falls into?
Encryption.
Encryption. Good. Is key agreement encryption? Why is key agreement different from public key encryption? Sounds like they're the same, but they're not. Yes.
For encryption, you choose like your ciphertext or your plaintext, and then encrypt that.
Okay, but we could do that with Diffie-Hellman, right? I could run Diffie-Hellman with you and then encrypt some stuff with the resulting thing. What is the difference? Yeah.
The key is not going through a channel, a communication channel.
Good. There is a communication channel there,
Yes,
but
but we're not exchanging the private key, like one key we're not exchanging.
good. It's a non-interactive process. So the idea is that I can send you a single message, one flight of data, and that's what public key encryption gives you, is the ability to like email you something. With Diffie-Hellman, can I email you something? No, because first you need to send me like an email with your G to the A, and then I need to send you like my G to the B, and now we can like communicate. It's interactive, fundamentally interactive. You need to generate a new G to the A every time we do this. So public key encryption is a little bit different in the sense that it doesn't have that interaction. Okay? And what is the third type of protocol that we can build in this public key world that we've talked about a lot, haven't really defined, but is very important? Yeah.
You mean like we use like those kinds to exchange like a session key?
Well, we could build higher level protocols out of these, but I'm thinking of something different.
Oh.
Remember when we were talking about symmetric crypto, we had encryption and we had authentication. What is the authentication equivalent? You guys have already mentioned this, I know you know it, in the public key world. Signatures, good. So fantastic. So these are kind of our three most important primitives. When we're over in the asymmetric, by the way, asymmetric and public key mean the same thing, meaning the keys are not the same on both sides. Okay, so signatures. And these provide authentication. All right, so I want to very briefly, we've already talked about key agreement too much. I want to just kind of give you an idea. What is the API? Without getting into the details of RSA or Elgamal or specific schemes, what does a public key encryption algorithm look like? What does it consist of? What kinds of algorithms? If somebody says they've invented a new public key encryption algorithm, PKE, what kinds of algorithms should I look for? They're going to say, this consists of 14 algorithms. And you're going to say, 14 algorithms? What are those 14 algorithms? How many algorithms should I look for? Okay, let's say you have one algorithm which is going to do something that actually generates keys. Okay, so we need at least one algorithm, right? So this is going to consist of at least one algorithm, which we're going to call the key generation algorithm. Okay, we're not going to get into the details of what it takes in and what it takes out, but this will output what? If it's a public key encryption algorithm, yes?
A public and a private key?
Good, it will output a PK, and I'll call it a secret key SK. So we have one algorithm, always has to be there, yeah?
Now the second step would be like somehow the key exchange, or how the partners can. Like,
No key exchange. It's public key encryption. Right? If you give me your public key, that part we don't have to model.
Yeah, sure, but we're generating a public key and a private key, but
Mhm.
still, like the other party needs the public key to.
I posted on my website. We don't have to include that here.
Okay.
Okay? So don't worry about that. So we have an algorithm for generating the public and the secret key, and I put my public key on the website, and you're going to encrypt to me. Whoa. Shoot.
No science.
Go ahead, back there.
I was gonna say like encryption.
Good, we need an encrypt algorithm. I kind of foibled that one. All right, so encrypt. What is the input to the encryption algorithm? What values are you going to pass it?
Public key and data.
Good. Public key and a message. Very good. And what's it going to spit out? Very good. PKM, and it's going to spit out a ciphertext. What is the next algorithm we need in a public key encryption scheme?
Decryption.
Very good. Give me the inputs to your decryption algorithm.
Private key and the cipher.
Okay, sorry, say it again.
Secret key.
Secret key, okay, good. Secret key, and you said something else?
Cipher.
Ciphertext, and what do I get out?
Plain text.
Plain text. Or if it fails, maybe it gives me like an error code. Use bot for error a lot of the time, okay? Good, so this is your typical, in fact, this is the formal definition of what a public key encryption algorithm is. 3 algorithms, one for generating keys, one for encrypting, and one for decrypting. Okay. How, forgetting about, like, so not forgetting about, so keeping this in mind, how do we build an actual public key encryption algorithm? Before I get into RSA, and I know you guys love RSA and you want to talk about RSA, we've already talked about Diffie-Hellman quite a bit. Okay, so Diffie-Hellman, is it a public key encryption algorithm? No, why not? Just remind me, I told you this 2 minutes ago, why not?
Because you can oppose your, what's that?
Yeah, in the standard Diffie-Hellman algorithm, every time we run Diffie-Hellman, it's an interactive process where somebody sends me a value, I generate another one. So I don't have a fixed public key that I can use for many different messages, right? What if I wanted to make Diffie-Hellman into a public key encryption algorithm? Could I do that? Yes or no? Maybe. Maybe. Good. We're up to maybe. What would I have to do? Don't worry if you think it's broken. Tell me. What could I have to do? Yes?
Fix G.
Okay, well, let's just say we fix, I agree, let's fix G. Good. And we also got a P value. We're going to fix that too. Let's just have that be. In fact, we can have the key gen algorithm generate those. What else comes out? So remember, Diffie-Hellman consisted of G to the A, G to the B, stuff down here, right? What do I have to do? So what is missing from Diffie-Hellman? Okay, every time I run Diffie-Hellman, both sides generate a new A and a B and just send messages back and forth. Okay, so this clearly does not work. I can't just post one thing on my website. what would you think might work if I wanted to just make it so I could post a single public key instead of having to make a new one every time I want to communicate with you? What might I try to do to Diffie-Hellman? What if I just send the same G to the A? What if I just fix G to the A and don't make a new one every time? Right? So if I want to send someone, I just send them always one G to the A, and then they just make a new G to the B when they want to communicate with me. Okay? So that gives us an idea. Is Diffie-Hellman secure if we do that? If we just fix one of the keys? So this is actually a question that was asked about 3 years after Diffie-Hellman was invented. A guy named Tahir Al-Gamal said, hey, wait a second. I'm going to write this down. El-Gamal. We used to spell it as 2 words. Now we spell it as 1. A guy named El-Gamal had the following observation. He said, what if I tried to make Diffie-Hellman into a public key algorithm where the key generation algorithm was just like Diffie-Hellman? So we would pick some G and some P, and then we would, select a random A from the set of, integers. Oops, it's supposed to be a V. Okay, we pick some A, and we output PK equals G to the A mod P, and SK equals A. I said, okay, great. We have encryption. We have a key generation algorithm where we always just pick the same G to the A. That's my public key for any number of messages you want to send. Okay, great. So we have key generation. How do we do encryption? What does encryption look like in this? How do we do this second algorithm? Okay, well, what do we know goes into an encryption algorithm? Okay, we know the public key. So if your public key encrypt takes in a public key and a message, all right, how are we going to implement this? What does the public key look like again? G to the A, good. So let's say we've got G to the A. Okay, we'll just call, let's say this, remember, is G to the A mod P for some user that we want to encrypt something to. What does the encryptor now do? How do you translate Diffie-Hellman into an encryption algorithm? Given G to the A, what do I do? What would I do in Diffie-Hellman? If you handed me a G to the A, what would I do? Good, so I have to pick a B, right? Good, all right. Pick B from the same set. These are P, great. By the way, this also should include, let's add, just for simplicity, let's add G and P to the public key so we don't have to worry about that. We generated it there. Pick B, what now? I've picked a B. I want to encrypt something to you. What do I send? If I send you G to the AB, I like your thinking. You are in the right neighborhood, but I'm worried that that might not be the best idea. What is G to the AB in the Diffie-Hellman protocol? The secret, right? We don't want to send the secret over the wire. But we definitely, I like your idea of deriving G to the AB. What do we actually want to send as a ciphertext that our bad guy can see?
I mean, you encrypt them with G to the A.
I like it. Very good. So we somehow, I'm going to put a big somehow here.
Yeah, I'm not sure.
Somehow encrypt. We'll come back. We'll revisit. M with G to the AB mod P. I'm not going to write it. Too lazy. Okay, we have to send somehow. Let's call this value, I don't know. Let's say this is X. Okay, somehow we've encrypted it. Don't worry about how. We have to send one other thing as part of the ciphertext, though. We're missing something.
G to the B.
Ah, good. We have to send G to the B because that's what we send in Diffie-Hellman. Okay, so we send, or sorry, let's say output the following 2 elements: G to the B mod P, G to the B mod P, comma, this value X that we made in the previous line where we kind of don't have a plan for how we do that yet. Does that sound good? I know my handwriting sucks. Make sense? All right, good. Finally, what does our decryption algorithm look like? Okay, decryption takes in what? Wait. What does decryption take in? The ciphertext and what? Wow, is my handwriting that bad? The secret key. What's the secret key? If I'm the person who sent G to the A, my public key was G to the A. What's my secret key? A. Remember. Okay, so remember here, SK equals A, the integer A. Okay, so we decrypt. We take in our secret key, which is A in this world, and the message and the ciphertext. What was the ciphertext? The ciphertext was this weird thing where we have G to the B, comma, X. Okay, so this is our decryption algorithm. Okay, we're going to parse that ciphertext. Now what are we going to do? What's the first thing? We know we're going to have to compute something. What are we going to compute?
G to the A.
Good, okay, great. I love it. Compute G to the B, which we take from here, raised to the A. Fantastic. Now what? What do we do with that?
Decrypt X.
Somehow decrypt X using G to the BA. Fantastic. We've built a public key encryption scheme from Diffie-Hellman. Maybe. We're missing some stuff. How do we do this somehow stuff? How do we encrypt a message using that? Yes?
Just use like a yes or something.
Okay, good. So one answer, which is actually a real answer, is we take this G to the AB stuff and we use it as an encryption key for something like AES, or CBC mode maybe AES, and we feed that G to the AB stuff into AES and we encrypt whatever message you want. It does work. It happens. This is actually one way people do it. One little detail, just an engineering detail. Let's say my Diffie-Hellman parameters are 1,024 bits long. My P is 1,024 bits long. How big is G to the AB? Also 1,024 bits long. How big is an AES key? Yeah, that seems like a little problem. What could we do to maybe make that a little bit more? What can we do to G to the AB before we feed that into AES?
Hash it.
Okay, yeah, good. So we could use some kind of function like a hash function to take G to the AB and hash it down into an AES key. And now we use AES to encrypt. That is legitimately fine. This is not what Al-Gamal did, but it is something you could do. What else could we do?
Run multiple rounds of AES.
Let's pretend that AES, it's 1981, and you're Tahir Al-Gamal, and AES has not been invented yet. And you just have a few tools, right? You've got this exponentiation thing. You've got multiplication in this group. And you don't want to use any other fancy stuff like block ciphers or hash functions. Turns out that this somehow, one way you can do it is what you guys all just said, which is using AES. That's fine. Turns out that there is another nice trick you can use with later these, right? So what you can do is you can compute X is equal to G to the AB times the message. If you make the restriction that this message must be in the set, 1, P minus 1. Okay, so the argument here, believe it if you want or not, is if it was the case that G to the AB is indistinguishable from a random element of the group, and we multiply a random-ish looking element of the group by your message, which has been encoded as another element of that group, if this was truly random, what would be the distribution of X?
If you random distribute between the P digit, if you random distribute within your group.
Yes.
Isn't that also a kind of hash function? Multiplication by a randomly large?
It's not necessarily collision resistant, so it's not necessarily a hash function. So if I were to do, let me say I presented it to you like this. Let's say I had some random value and I XORed it with a message. What would you guys think when you saw that? What primitive would you immediately think of? One-time pad. And why? Why, if this was perfectly random and the same length of the message, would we argue that the one-time pad was secure? What was the argument for security of the one-time pad? Yes?
Entropy?
But more just intuitively.
Every potential plaintext message is just as likely as the other.
Good. If this is randomly distributed, and I give you the XOR of these two values, right, and it could be the encryption of any possible plaintext. Okay? Now let's say I give you something like this. Let's say I give you some random group element. So this is R in the group, and M is now also in the group, and I give you R times M. This is the group operation. Based on the little bit we know about abelian or cyclic groups, what could we say about this value? What's that? It is definitely in the group. But what could we say about the security of it?
That it's that having that result doesn't give us any information about the underlying message.
Good, exactly. What it means is that if I give you this thing, and it's a certain type of group, then for every given this encryption, then basically there exists a value R for every possible message that would allow you to decrypt that to a different thing. So it's basically the same as the one-time pad. So what El-Gamal realized is if everything was set up right, then, and this was indistinguishable from random, which he would later prove, then just multiplying these two things together would give you a strong encryption scheme. And similarly, over here, decrypt X becomes what? If I take in X and I've computed G to the AB, what do I do? I now have this value, which is X, and I want to compute the message from it. How do I undo this? Divide. Do we get division in groups?
Find the inverse of G to the A.
Find the inverse. Good. So we compute M is equal to X times G to the AB to the -1. Good. So we just do that, which we often write as division, but it's okay. So good. This is basically what El-Gamal's scheme was. Now there's some hiccups in El-Gamal's scheme, and we'll come back to those a little bit later. It turns out that there are some problems. If you pick the wrong group, you can actually have some problems. But this is basically the intuition, is that public key encryption, once you have Diffie-Hellman, you can just reuse one public key, or one Diffie-Hellman value as a public key, and then you get public key encryption almost for free. Now the weird thing and the sad thing is that El-Gamal did not come up with his scheme until like 1981 or 1982. And something happened a few years before that that actually defined what public key encryption is for most people. And you guys probably know what that is. It has 3 letters. It's RSA. And so for years and years, people thought the only public key encryption, they knew about Diffie-Hellman, but they thought it couldn't be used as a public key encryption algorithm. And so they went back and they basically said, well, the only public key encryption algorithm in existence is this thing called RSA. How does RSA work? Can anyone give me a quick overview of how that public key encryption algorithm works? Does anyone have any knowledge about RSA? Yes. How does it work?
What exactly, like the generation of the keys, or how it is encrypted?
What do you guys know? Tell me any fact about RSA.
So one fact is to encrypt, we use like the same thing, like oh no, it depends. So if I'm the sender and I want to decrypt or encrypt, for example, my message, I use my private key and I encrypt the plaintext, and I just send it to the receiver and he uses my public key.
Wait, now you're confusing me, because I thought we agreed that public key encryption always looked like this. So the encryption, when I want to encrypt to you, I get your public key and I send a message.
You're right, but when I'm sending a message to you, I use my private key.
Ah, interesting.
Is that like that?
No. but I can see where you might be getting that from, because you can use RSA with a private key, but we'll come back to that. It actually gives you signatures.
Oh, okay.
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 So with RSA as a public key encryption scheme, does anyone know who invented, what does RSA even stand for? Let's start there. Yes. Very good. Okay, these 3 guys who basically were fooling around with number theory, which everyone used to say could have no possible application to anything in the world that mattered. And these guys were thinking about how to build a thing called one-way functions, functions that were easy to compute in one way and hard to compute in the other way. And they came up with this idea. And the idea is that they were looking at one particular problem. The problem we've already talked about is the discrete log problem. We've talked about that a lot. The problem they were looking at is the factoring problem. And the factoring problem, can somebody tell me what that is?
Breaking a number into its prime factors.
Okay, great. So more specifically, they were looking at basically composite numbers, and they were composite numbers that they'd constructed. So they were basically saying, okay, let's reduce this to a slightly simpler, not any composite number, but let's imagine that we pick two primes, P and Q, and they're large. Everything in crypto is large. You can't have this be like a 3-digit number. Okay, so P and Q, and then we compute some product, N equals P times Q. Okay, the problem that they were thinking about is we know that it is, at least as far as we've been able to find, relatively easy to multiply two large numbers together. We have fast multiplication algorithms for doing that. But so far, we have not found a polynomial time or efficient algorithm for given an n made from two random prime numbers, going back and finding P and Q. This just seems to be a fundamentally hard problem. If it wasn't, we'd be in big trouble. Okay? So this was the problem they were looking at. The problem was, though, how do you use this problem to actually encrypt stuff? Remember, public key encryption, we don't just need a hard problem, we need an algorithm for encrypting. And it turns out that the algorithm they came up with was a little goofy, but I'll show you what it looks like. Okay, so in RSA, we have, as in every public key algorithm, we have, let me erase that properly. We start with a key generation algorithm. Okay, we've already kind of talked about part of what we're going to do in this key generation algorithm. Step one is clearly that we're going to pick two large prime numbers. Pick large primes P, comma Q. Okay? And then the next thing we're going to do is we're going to compute the product. N equals P times Q. So far, so good. But we have to do something that allows us to actually encrypt with this. And so what they realized is that it would be possible, I'll show you what happens with this, we can pick a random integer, E, which has the property, and I'll explain what this is, with the property, I don't know why I'm writing with property, but with property, that G, greatest common divisor, of E and a special function called phi of n is equal to 1. So phi of n is actually it's called the Euler-Tosche function. And this is a function that, in the case of this particular composite, can be computed as basically each of the prime factors of a composite number subtract minus 1. So phi of Rn is always going to be equal to P minus 1 times, oops, I'm running out of space here, times Q minus 1. Okay, and this Tosche function essentially tells us like the size of the underlying group underneath n. So if n was a prime, then this would literally be equal to that prime minus 1. That would be the order of the group. When n is a composite, we get P minus 1 times Q minus 1, because there are two prime factors of n. Okay? Don't worry too much about why we pick E this way, but let's just go here and let's assume that's the case. I'm running out of room. Shoot, I guess I'm going to have to erase my KE over here. Okay, there's one other step, and the step is as follows. We now, step 4, want to find one more value, which we'll call D, and it has to have the following very important property, which is that E times D is congruent to 1 mod phi of n. And there's an algorithm we use to do that. It's the extended Euclidean algorithm, and this is in the book. You can actually see how to implement it. Just trust me that we want to find D with this particular property. Finally, when we output the public key, what do you guys think is the public key here? Any guesses? Yes?
The encryption key.
Good. And what values? Which of all these crazy things we've computed formulate the public and the secret key?
The E is the public key.
Very good. Okay, so output PK equals, definitely includes E. What else? There's one more thing we need to throw in there. N. Very good. Okay, what's the secret key?
Z.
Wait, where do we get Z? Is my handwriting that bad? It really is that bad, isn't it? D. D is the secret key. we actually can throw away PQ. We don't need to keep them. We can keep them. They're optimizations for decryption, but we don't need to keep them. Now, what these folks, R, S, and A, realized is that if you produce a public key that has this particular structure, then there's a very interesting set of properties. You can build an encryption algorithm that looks like this. The encryption algorithm, remember, takes in a public key and a message, and we're going to require that the public key consists of n, comma, e from over there, and the message is basically a number between 0 and n minus 1. And what we're going to do now is we are simply going to compute one very easy function. We are going to compute m exponentiated to the e mod n. Okay? And that will give us our ciphertext. And that's it. Output C. How do we decrypt this? So if somebody has encrypted a message C to me, how do I decrypt it? Using my secret key.
C to the power of D.
Good. Why? Why does that work? Why would that decrypt my message?
Because of our property 4.
Very good. And it happens to be the case. Decrypt SK, comma C, where this is equal to D, and this is the output of that algorithm. Right? To decrypt, the beautiful thing here is we simply compute M is equal to C raised to our D, also mod N. And the reason that this works is you could rewrite this as M is equal to, if you break open the C, M to the E raised to the D. And because the way you can think of this is the exponentiation that happens in the exponent is computed mod phi of n, which is essentially the order of this group. And so this reduces to m to the 1 because we made the restriction that e times d mod phi of n is always going to be equal to 1. And because of the property that exponentiation, any kind of multiplication that happens up in the exponent is computed mod phi of n. Basically, the e, anytime we raise something to the e and then we raise it to this d value subsequently, we recover the original message. And that is how RSA works. Now, is RSA a good encryption scheme? How do you break RSA?
If B and Q was relatively prime.
Well, what do you mean by relative? I mean, they're both prime, so they're going to be relatively prime. But like, what could we do to break this encryption scheme? Yes?
Yeah, in a way that can efficient factoring the thing.
So if I could factor, if you give me your public key, which is n comma e, and I build a giant computer that can factor your n, maybe it's a quantum computer, what can I do to you? Right, so I can take your n and I can recover the primes p and q. What can I do to you? What can I do now? Yeah.
And you know phi of n, so you can calculate
Good.
another d.
Exactly. In fact, I can compute the same d, right? Because it turns out that there's exactly one d for every e. Just happens to be a mathematical fact. So basically, if I can compute your p and q, then I can always recover your secret key, and then I can basically do decryption. So basically, in this case, breaking the factorization problem, being able to factor these large numbers, would imply that RSA is broken. Does it work the other way? Does the hardness of factoring imply that RSA is secure? Can we show that if somebody was able to break RSA, they would be able to factor large numbers? You want to think that. You want to think these are the same problem, but they're not, actually. It turns out that it's definitely the case that breaking factoring would break RSA. RSA is secure under a problem, and this should be familiar with you, a mathematical assumption that we call the RSA problem. And basically, the problem is, given this value m to the e, could you recover the value m? And that's not quite the same as the factoring problem. You can't. If I was able to build a box that could always somehow solve this problem, that doesn't necessarily imply that you could always break factoring. There are schemes that are equivalent to factoring. RSA just isn't one. One of the interesting things that's historically neat about RSA is it actually wasn't discovered by RSNA. It was discovered by British intelligence mathematicians at GCHQ about 3 years before. They discovered all this, and they actually created this. I think it was Cox and Ellis. They came up with both Diffie-Hellman and RSA, and then the British government immediately classified all of this stuff and never revealed it. And so 20 years later, or 30 years later, it all came out that they invented this stuff. But RSA got the credit because they were the ones to do it publicly. All right, so we have RSA. What do you notice about the RSA encryption algorithm? Now, when we talk about semantic security, the idea that you can encrypt something such that nobody can tell what's in it, what was the one thing, what kind of scheme did we say could never be semantically secure?
Deterministic one.
Yes. Now look at the RSA encryption algorithm, not the key gen, the encryption algorithm, wherever I put it up there. Is it deterministic or randomized? You don't have to whisper, you can just say it. Good, it's deterministic. So could RSA be semantically secure? No, it can't be, because fundamentally you could always play the IND-CPA game, you could always win. All right? What does it mean for RSA to be secure? Well, how do we add randomness? Maybe we could do something like add a random string or something to M. We can do things like that. I'll come back to that in a second. What else do you notice about RSA? Now, if we were to take RSA, and I was to, let's say, if somebody was to give me an RSA ciphertext, a message raised to the E mod n, and I wanted to do something to change that message. If I change the ciphertext, maul the ciphertext, so that it would decrypt to a different message. Maybe I want to multiply it by 2. Can anyone see a way I could do that? What could I do to a ciphertext to cause it to change in a meaningful way? All right, how could I multiply? Let's say somebody gives me C. What can I do to C to force it to be multiplied like this? Okay, so what we can do is the following. So if you give me C, I'm running out of space. C is equal to M to the E mod n. What happens if I compute C times 2 to the E mod n? And then I send that to you to be decrypted. Okay, well, you're going to decrypt it. You're going to raise C to the D, which gives you back M. And you're going to raise this to the D, or the whole thing's going to get raised to the D, sorry. You're going to raise the whole thing to the D. And this is going to give you back 2. And so now you've basically computed, by raising this thing to 2 to the E, you've taken the underlying plaintext and you've multiplied it by 2. So the point of this is that RSA, as its textbook explanation is given, and this is really the textbook implementation, has 2 problems. There is no randomization of the ciphertext, and secondly, there's no structure to the ciphertext, which means it's very malleable. I can multiply it by 2, I can multiply it by any number. This doesn't seem like a big deal until you think that maybe M is like the current income for AT&T Corporation, and I get a ciphertext and I multiply that by 2, or I divide that by 2, or something like that, and I'm able to change a ciphertext in a meaningful way. So if you had this RSA algorithm and you wanted to stop both of these attacks, what could you do to the message M before you encrypt it that would have a property of adding randomness and also preventing people from mauling ciphertexts? What might you do? What's that? A nonce? Okay, well, good. Like, you mean like a random string of stuff? Okay, good. I like this. So we're going to add some randomness to the message. I like it. So we'll have M, and we'll concatenate to it some R, which is a random string. Maybe this is a 128-bit random string. Okay, so this means that our message is a little smaller, because we have to fit this all into a 1024-bit number, for example, but that's fine. We can afford 128 bits of random stuff. And this does actually seem to solve our randomness problem. Now, every time I encrypt the same message, I can use a different random nonce, random string, and I'll get a different ciphertext. So this is good. Probably gets us a lot closer to CPA security. But doesn't necessarily solve our malleability problems, because somebody might still be able to multiply this value by something and cause it to change in a way that would change the message to a meaningful value. Yes?
In order to protect integrity, you should just use a MAC.
With what key? It's a good question, but remember, the idea of public key encryption is that we don't share a key. I have your public key. Macs require that we share a secret key. I need a secret key to make the Mac, and you would need a secret key to verify the Mac. I like your thinking, but we don't share a key. Yeah?
Like you put nonce for the end of the message, and also you set the nonce to the receiver, and the receiver can decrypt the message if the end of the gate the nonce is equal to the nonce that's set.
So that's pretty clever. I like that, except it requires me, I have to send an encrypted message to my receiver, but then I also need like another channel through which I'm sending the nonce. So you're saying like I'm sending this in plain text, the nonce?
Maybe?
Okay, I mean, it's an interesting idea, except what if the attacker can change that plain text nonce and also maul the message in some way? Like, it doesn't necessarily guarantee that you won't. I don't know if that could work. I don't think it does necessarily work if it's in plain text, because the attacker could maybe change that too. The way that this is actually done in practice is using something that's even simpler. There are two ways. There's the bad way and the good way. The bad way, which is unfortunately how TLS does it and every real protocol that you guys, and GPG, is you put on a flag. And by flag, I just mean a fixed sequence of bytes that are always the same, they're structured. And the idea there, the hope there, is if somebody is able to multiplicatively maul this message, meaning they can take this whole thing, expressed as an integer, and multiply it. All they can do is multiply it by stuff. Then yes, they might be able to change M, they might be able to change R, which we don't really care if they can change, but they would also, in the process of doing that, mangle these bytes over here, so when it's decrypted, the check will not be right. And this is kind of, I think, what you were saying. Maybe it's very similar to what you were saying. But the idea is we just use a fixed flag. So we could have something like 0002, 0002 or something, and this could be our flag. And the hope is that it's very hard for people to maul the message to make that flag work out. The problem is that this is not true at all. It turns out that using this structured padding actually leads to some really, really bad attacks on encryption schemes. And there is another padding scheme, which I will probably have to show you next time because I don't have my adapter to show you the picture of it. But there is another padding scheme. So this is an example, by the way, of what we call a padding scheme. And a padding scheme is something that we apply to a message before we RSA encrypt it. Okay, this one over here is an example of a padding scheme which is called PKCS number 1 v1.5. It is terribly insecure. You can actually use this padding scheme to decrypt ciphertext because it's that bad. It has a padding oracle attack on it. The one that we should use is called optimal asymmetric encryption padding, and I'll show you a picture of that next time. That one uses a combination of hashing. It's not this arrow, actually. It uses a combination of hashing and adds randomness in a very clever way to make it safe to encrypt with RSA. And so RSA is basically, the system that we use most commonly, sadly, in many applications for doing public key encryption. Okay, what are the, what else is there to say about RSA? There are a lot of things you can do wrong with RSA. I made a list before I came to class, things that people have done over the year that are really terrible. So I said that we should pick a random exponent e, which would mean, technically speaking, it would be a large integer, maybe as large as n. But do we always, have you guys ever, anyone here ever looked at an RSA key in your life? Do you?
I think it used to be 3.
Why would we pick 3 as an exponent instead of a random one? You're right, but why? What's the advantage? Think engineering, think efficiency. Encryption is computing m raised to the e mod n. What's the advantage of computing e equals 3? Fixing e equals 3 and then picking d appropriately. D might be large.
It's a cheap multiplication.
Good. Computing things, cubing things, mod n, is really fast. Raising things to the blah, 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 blah power is very slow, or relatively slow. In fact, the cost of doing an exponentiation, it turns out, is basically linear in the number of 1s in the integer that you're exponentiating by. How many 1s are in the number 3 in binary? 2. So it's a very, very fast algorithm. So it's not very hard to do. Great. So 3 is very common, but 3 has some limitations. What happens if I take a small m? Okay, so let's say that I'm going to let me give you a really concrete example. Let's say that P is 7 and Q is 9. Okay, we're going to do the world's worst RSA. Okay, P equals 7, Q equals, my 7s look like 1s too. Great, P equals 7 and Q is 9, what is N? I'm literally asking you to do like 2nd grade multiplication in my class. What is N? Very good, N equals 63. All right, so what is, let's say I want to encrypt a small message. M equals 4. Yeah. Oh, I'm sorry. Oh my God. Why don't you guys tell me when I'm not thinking primes? 7 and 11. Sorry. 11 is a prime, right? No, it's hard being up here. You don't understand the pressure, right? So N is 77.
I mean, that would have made it the world's worst RSA.
Believe me, there are worse RSAs. My friend Nadia was telling me yesterday that she had found primes that were all powers of 2 primes. So it gets worse in real products. Okay, 7 and 11. We agree these are primes. N is 77. Very good. Now let's say my message is 4. So RSA encryption would be 4. Let's say we pick E equals 3 because we're trying to be efficient. That was a weird 3. Let's try again. Okay, 4 raised to the 3. We're going to exceed our, let's see. Okay, 4 raised to the 3 mod 77 is what? Somebody, quickly.
64.
Very good. Okay, now, can you invert that?
Yeah.
What? Why?
Because it's smaller than N.
Yes. Oh, that's weird. So the claim in RSA, roughly speaking, is that if m to the e is significantly larger than n, then what's going to happen to it is it's going to go around the modulus many, many times. And the assumption there, the RSA problem, is that if m is substantially large enough, if e is fairly large, then it's going to go around n so many times that we know of no fast algorithm for actually inverting it. But if it doesn't go past n, in other words, if m and e are small enough that it's not m times e, forgetting about the modular arithmetic, is actually less than n, then the actual thing, this is basically just equivalent to simple exponentiation. So for small exponents and small messages, RSA can actually be totally insecure. How do we deal with that? Well, one answer is don't use small exponents, use large exponents. That usually solves the problem. The other answer, which is one of the things padding gives us, is use padding to make sure that our message is never small. Tack a lot of bits, random bits onto that message, and that will always guarantee that even if you're using a small exponent like 3, you will always go many, many times around, or you'll be much, much larger than the modulus. And so these kind of simple attacks are not possible. But RSA with small exponents and small messages can actually be totally insecure, and this really does happen. People run into this. I already mentioned it's deterministic and malleable. Another thing people love to do, oh, this is people's favorite thing, is they love the idea. People, as soon as they see RSA, they say, you know what? I have 10 people. Why don't we just all use the same modulus, the same n? 10 different people. We'll have 10 different, one n, and we'll each pick our own e. And we'll have like this, great system. I don't know why they say this, but they've said this repeatedly. What happens? Does anything bad happen there? Yes or no? Is it possible to have 10 different people who are not trusting each other share a single modulus? Maybe there's some trusted party, some centralized party that will pick one modulus, and then we'll like calculate an e for you and an e for you and a different e for you, give you an ed. Is that safe? Turns out it's not safe. And the reason is, and the actual equations for this are in the handbook of applied crypto. If you know both E and D, you can recover the factorization of n. So anybody who gets both a public and a private key for a given modulus implicitly knows the factorization of the modulus, which means that if they want to find somebody else's D and they know their E, they can just do that easily. So common modulus is not safe. Every RSA encryption key has to have its own modulus. Can't share a single modulus across lots of people. And this turns out to be a problem in all sorts of fun ways too. Okay, so RSA. This is RSA. Pretty much out of things to say about RSA as much as I would like to. No, I'm not. I have 2 minutes. There is one amazing cool thing about RSA which we need to talk about. There were 3 things I told you I was going to talk about today. One was key agreement, one was encryption, public key encryption, and the other was digital signature. In the last 2 minutes, I want you guys to tell me what a digital signature scheme is. What is it? Quickly, it's 3 algorithms. Everything is 3 algorithms in crypto. What are the 3 algorithms?
Key generation.
Good, key generation. That is a good, I think you guys have learned enough that generating keys is important. Key generation produces a public key and a secret key. Very good. What's the second algorithm? Sign. Wow, you guys are getting faster. What does a sign take in? Secret key, right, because it's asymmetric, we need the secret to sign and what? A message? Very good. And spits out what? What?
Sign message.
Well, let's say a signature, which I'll write sigma. I like sigmas. Okay, and what is the last algorithm?
Verify.
Very good. We need a verify algorithm, and what does that take in? Public key, and what? And the message, and sigma. And what is it output? What? True or false? Since we're, computer scientists, we'll say 1, 0. Okay? So verify. This is the basic outline of what a public key signature algorithm looks like. Before you get up, what happens if you can think about this, what happens if I don't encrypt with the public modulus, the E? What happens if I take a message, instead of computing M to the E mod n, I take M to the D mod n? And my claim is that this is actually, if you use your secret modulus to encrypt a message, what you actually get here is a signature on the message. And how do you verify that signature? If somebody gives you M and this value, sigma, what is the verification algorithm?
Sigma T.
Yes. The verification algorithm is simply a question of taking sigma to the E and comparing it and seeing if it's congruent to M mod n. And with a lot of caveats, it turns out that the really nice thing about RSA is the minute you have RSA encryption, with no extra work, you instantly get a signature scheme. You need to do some extra stuff, like add padding to the signature scheme to make it really secure, but you get both signature and encryption out of RSA. And now I'm out of time, you guys can go.